Large concept models (LCMs) and large language models (LLMs) represent two distinct approaches in artificial intelligence. While LLMs focus on generating human-like text, LCMs integrate structured knowledge to reason over complex concepts, making them more suitable for specific applications. LLM use the concept of tokenization, where text is broken down into smaller units called tokens before being processed. These tokens can represent words, subwords, characters, or even byte pair encodings, depending on the tokenizer used. They try to predict the new tokens that best fit the context of the current situation. LCMs excel in structured knowledge integration, allowing them to reason over abstract concepts like causality and ethics. This concept enables LCMs to provide more accurate and contextually relevant insights compared to LLMs, which often generate plausible but unverified information. LLMs often struggle with surface level understandings and can produce biased outputs due to their training data. In contrast, LCMs address these limitations by utilizing structured knowledge bases and ethical frameworks, leading to more robust and fair reasoning. LLMs rely on statistical correlations rather than deep conceptual understanding. They predict text based on probability rather than true comprehension.
Structured knowledge integration in LCMs. Large cognitive models integrate structured knowledge using knowledge graphs and ontologies, allowing them to reason over complex concepts. This structured approach enables LCMs to go beyond pattern recognition and instead make informed inferences. For example, in biomedical research, LCMs can accurately link genes to diseases, facilitating better diagnostics and drug discovery. Reduced hallucinations (LCM versus LLM). One major limitation of large language models is their tendency to generate hallucinations, confident but incorrect responses based on statistical patterns rather than real knowledge. LCMs overcome this by grounding the response in explicit knowledge structures, significantly reducing misinformation. This makes LCMs more trustworthy and reliable, especially in high-stake domains like healthcare, finance, and legal reasoning. Cross-domain reasoning capabilities. LCM excel in connecting concepts across different domains, a critical feature for interdisciplinary fields. Unlike traditional models that struggle with context switching, LCMs perform multi-hop reasoning, allowing them to diagnose rare diseases by linking genetic, environmental, and clinical factors, model climate change by integrating data from physics, ecology, and socioeconomics, solve complex business problems by synthesizing insight across finance, logistics, and operation. This cross-domain ability makes LCM far more powerful for real-world problem solving. Technical superiority of LCMs. Compared to LLM, LCM offers key advantages. First, knowledge retention. They don't just memorize, both understand and retain the structured knowledge over time. Second, multimodal flexibility. They seamlessly integrate text, images, graphs, and tabular data, enabling richer insights. Third, explainability. Unlike LLMs, which function as black boxes, LCM can justify their reasoning with clear, traceable logic. These factors make LCM the next evolution in AI, better suited for complex real-world decision making.
LCMs provide structured and auditable reasoning chains, ensuring that each step of the decision making process can be traced and verified. This transparency makes it easier to understand how conclusions are reached, facilitating debugging, compliance, and trust in critical applications such as healthcare, finance, and decision making. On the other hand, LLMs generate outputs using complex statistical patterns learned from vast amount of data. While they can produce highly sophisticated and contextually relevant responses, their reasoning is often opaque. The lack of explicit reasoning chains make it challenging to determine how and why a particular output was generated, raising concerns about reliability, accountability, and interpretability, especially in high stake scenarios. In medical diagnostics, LCMs excel by mapping symptoms to underlying pathophysiological concepts, offering clear causal explanations that aid in accurate diagnosis and treatment planning. Their structured reasoning ensures transparency, making it easier for medical professionals to verify and refine decisions. In contrast, LLMs rely on probabilistics associations, making their diagnostic reasoning less interpretable. Similarly, in education, LCMs enhance learning by linking complex concepts in a structured manner, ensuring students grasp foundational knowledge before progressing. This structured approach fosters deeper understanding, whereas LLMs may provide contextually relevant but sometimes surface level explanations without clear reasoning paths. When to choose LLMs or LCMs? Choose LCMs when tasks require accuracy and traceability over fluency, such as in legal analysis or drug discovery, where every decision must be logical, justified, and verifiable. In legal contexts, LCMs ensure precise argumentations by mapping laws, precedents, and case facts systematically, reducing ambiguity. Additionally, LCMs are ideal for interdisciplinary reasoning, making them particularly valuable in complex fields like climate science and policy design, where multiple variables interact in structured ways. AlphaFold has revolutionized protein folding by leveraging biological knowledge graphs to predict protein structures with unprecedented accuracy. By integrating vast amount of biochemical and genomic data, AlphaFold has addressed a long-standing scientific challenge that once required costly and time-consuming laboratory experiments. Its success demonstrates how structured, rule-based approaches can outperform purely statistical methods in solving complex biological problems, enabling breakthroughs in drug discovery, enzyme engineering, and disease research.